not answering. Oh, am I on mute? I'm sorry. Were you talking to me and I just couldn't hear you?
Oh no, I didn't have any questions.
Okay. I forgot I didn't unmute. And let me put the chat up. I was like, man, Kiana's so quiet today. And it's hard to hear you when I have my computer on mute. Anyways, okay. Could you hear us chat though?
Yeah, I could hear you guys fine. I didn't have any questions either.
Okay. Alrighty. So where we're at, we're going back into thermodynamics. And do you guys, I don't know if I'm showing my age. You ever watch the show The Big Bang Theory? Yeah, and who's your favorite character? Sheldon. Yeah, Sheldon, he makes the show. Yeah. Yeah. Oh, really? Oh, I didn't know that. Yeah, Jim Parsons, I think his name is. Yeah. Anyways, like so I mean Sheldon, if you know the show, he's just a very awkward, scientist. And like I mean, unfortunately, there are people like that in science, and one of them, probably even worse than Sheldon, was a guy named Gibbs. And Gibbs, he was just like he is absolutely brilliant. I mean, it's very rare that you see this level of brilliance, and we can go through and we'll talk a lot today about some of the stuff that he did and he discovered. But I mean, he also he basically like sat in a basement in a dark room and did calculations and derivations. That's all he did. And like I mean, so in academia there's a lot of politics, not surprisingly, there's politics everywhere, and people hated him. He was socially awkward, and really socially awkward. And I mean, surprisingly, another one like that, if I know this is kind of a slant, conversation, but apparently another person kind of like this, Thomas Jefferson, one of our founding fathers, apparently he was a terrible speaker. I mean, we don't have any of his voice recordings, but apparently a really nasally way of talking. Like he, like the State of the Union address, right? That the president always gives to Congress. He always wrote it and sent it to Congress and had it read aloud because he didn't want to deliver it. So he hated speaking. He hated talking to people, kind of thing. Although, I mean, he had an interesting life, went to France and, but Gibbs, going back to Gibbs, like personality wise, this guy apparently was horrible. And although he had a very powerful ally, so the Lord Kelvin was his ally. Lord Kelvin, of course, from the Kelvin number scale. And back in the day, like, to be a scientist was kind of an aristocratic thing. So someone like me, like an instructor, I would be viewed almost like a circus performer. So like, kind of like when you had instructors, frequently they would like pass a hat and kind of in like, I would be tipped. I would like work off of tips kind of thing. Like, and so you either like a circus performer or you were like a nobleman aristocrat kind of thing. And Lord Kelvin was a nobleman aristocrat, and was very successful, at least, among other things. And Gibbs, not so much. I mean, he was, like I said, he was brilliant, and he was barely scraping by. And he, and the legend has it, I mean, there's a lot of legends in science, but legend had it that Lord Kelvin went to a faculty party, and of course people are like, oh, Lord Kelvin, and, kissing up to him kind of thing. He's like, yeah, where's Gibbs? I'm like, Gibbs? Like, he's the weirdo in the basement, just let him be. I hate talking to him. He's like, no. I really want to talk to him. It's like, have you seen his work? It's brilliant. I'm like, what? It's like, we're not gonna look at his work. He's so weird, but Kelvin looked at his work. He thought it was amazing. And he forced Gibbs to come out of his hole and extolled him. And then after that, after the approval of Lord Kelvin, Gibbs was granted tenure and title and that kind of stuff. Because when you get tenure, like I'm tenured, so that means like I have a title. I mean, titles mean nothing in the United States, of course. I like Picard. I like Patrick Stewart. He's Sir Patrick Stewart. For instance, and so they have titles in England and that kind of thing. And so I have a title. My title is professor because I'm tenured. So it's in a way it's well, not quite a knighthood. Knighthood is much more important than a professor. But I mean, it's like that. You get a title, kind of thing. So because of his relationship with Lord Kelvin, or not relationship, but the approval of Lord Kelvin, it really helped Gibbs. And like I said, Gibbs, just an awkward dude that just sat around and did, I shouldn't say just sat around, but he would do derivations, and he discovered, I mean, the stuff he discovered is amazing. So, and what Gibbs did, he invented a term, and he called it, he named it after himself. And the Gibbs is known, the G is H enthalpy minus temperature times entropy. So remember enthalpy, that's the heat of reaction. So when a chemical reaction happens at a constant pressure, the enthalpy is how much energy is available. And temperature, that's, we're familiar with temperature, average kinetic energy. Right. So, and then S, entropy is the number of equivalent states. So remember that the natural log, the Boltzmann constant times the natural log of the states. So, and even more importantly, change in Gibbs energy. So also known as free energy, the energy available, the free energy available is the change in enthalpy minus temperature times the change in entropy. So this tells you, and like I said, it's really cool what Gibbs did. Tells you a couple things. When delta G is negative, that means that the reaction is spontaneous. The reaction or process is spontaneous. It means it's going to happen. If delta G is positive, it means it's non-spontaneous. It means it's not going to happen. And if Gibbs energy is 0, that means that the process and or reaction is at equilibrium. So this is really cool. This is really cool because it saves you so much time. There's a saying in science also, a day in the library will save you a month in the laboratory. So meaning if you can go and you can figure things out, so doing some calculations, you can right away figure out if the reaction is going to go, if it's not going to go, or if you're at equilibrium and nothing's happening anyways, kind of thing. So that's really nice. So let's explore this a little bit more. So change in Gibbs energy is equal to the change in enthalpy minus T delta S. So remember, negative, when something is negative, it means it's going to happen. So let's talk about the situation where delta H, so this quad, and I'm just showing you this graph, and I always thought this graph was kind of cool. I don't think the textbook goes over this, but I remember seeing this. I thought this was interesting. So when you have a negative delta H and a positive delta S, so if you have a reaction or process that's exothermic, it's releasing energy, and you have a situation where the entropy increases, this means that it's always going to happen at every temperature, under any condition, it's going to happen. But remember, we don't know how fast. That's the limit of thermodynamics. The limit of thermo is it won't tell you how quickly the reaction is going to happen. It just tells you if it's going to happen or if it's not going to happen. So you will know right away if the process is exothermic, which is negative delta H, and if the entropy increases, it is always going to happen under any circumstance. You just don't know how fast. Then look at the other way around. If you look at this quadrant here, so I'll go ahead and put the S there. So you have positive delta H and you have negative delta S. So if it's endothermic and the entropy is decreasing, that means it's never going to happen. This is never going to happen at all. So some other circumstances, so like this quadrant here, so low temperature, this is when entropy goes down, but enthalpy is negative. So there are some processes that only happen at low temperature. An example of this is like ice freezing. So a process like this, so when ice freezes or when steam condenses, when both of these processes happen, it's exothermic. So, right, if you've ever taken, like if you've put your hand over steam and the steam condenses, it hurts, right? It hurts because the latent heat is giving off. So it's exothermic. It's really exothermic. Delta H is very negative, but you're going from water vapor to liquid water. So the entropy is going down. And how is it possible this happens? Do you remember that the delta S surroundings, it's going to be, it's minus delta H over temperature? Do you remember that? We talked about that last class. The idea though is the entropy for the universe. So remember the second law of thermodynamics, entropy is always increasing. So by the fact that the enthalpy is negative, and even though the system's entropy is decreasing, the overall entropy of the universe is increasing because of that transfer of enthalpy H energy and that transfer to the surroundings. So the second law of thermodynamics is still valid. So, and believe it or not, this argument came into be in the intelligent design argument. Are you guys familiar with intelligent design? The idea that a higher power designed the universe. And mind you, I'm also religious, so I myself am Catholic. I never saw a creationism versus intelligent design versus just knowledge. I personally never had a crisis of conscience for that. But I did think it was amusing that the discussion ended up involving thermodynamics. And one of the arguments for a creator was, well, you know, the universe did not form, it was created because, like, look at us humans. We humans are very structured, right? We have very structured cells. We have very structured DNA. There's viruses that are very structured. That's a break in entropy. Like, how could something have formed without some sort of intervention to change the entropy? And the counter argument was this equation right here. That in forming, like, even though we're in forming and also to maintain, for me, myself, to maintain this amazing, beautiful form, you know, now that I'm being recorded, I can say that. So in order to maintain this amazing form, I have to eat. And as I'm eating, I'm releasing carbon dioxide, water, and energy. But the amount of energy that I'm releasing is much more than the entropy lost to keep my cells all structured. And of course, you guys are beautiful machines as well. So even those on Zoom land too. So Kiana, you have a beautiful machine. So we all have beautiful structured machines, but as we're, you know, maintain our machines, the entropy of the universe is still increasing because of the heat flow. So that's an example of process there. So negative enthalpy, but entropy is going down. So this works at low temperature. And look at the other quadrant, high temperature, when delta H is going to be endothermic, but entropy goes up. So an example of that is atomizing something. So like, let's take my cell phone, for instance. My cell phone right here, it's a solid and it's very structured. And, so entropy wants to take all these atoms and just fly them out of there. Entropy suggests that this is too ordered, this is too structured. Entropy wants it to go away, to scatter itself. It doesn't want to be this ordered. What's keeping it together? The enthalpy, the bonding. In order to break the bonding, it requires energy. So if you put enough energy into this, so if I took this cell phone and I threw it in the sun, what's going to happen? Yeah, it's going to fly apart. So if you put enough energy into this, that it'll eventually, the atoms will just break apart and fly away. And that's the example here with a high temperature, where you need to have energy to break the bonding. And the bonding is what's keeping the item structured. But if enough energy goes into it, entropy will this T delta S term will take over, and the T delta S term will overcome the delta H term, and then the item will fly apart. So that's the idea with thermodynamics. So does that make sense? Anybody have any questions? So, all right, and this is not in the book, but I like to allude to future classes. So entropy is a state function. Actually, there's lots of state functions. So we've learned about a few: internal energy, enthalpy, entropy, Gibbs. There's others. It's Helmholtz free energy is another one. We don't talk about that in this class. But these are all state functions, which means they're path independent. So work and heat, those are not state functions. Those are known as path dependent. So, but state functions, they are path independent. What that means, when you study more calculus, you'll learn about exact differentials, which means that a function, if you have a partial differentiation with respect to one variable and a partial differentiation with respect to another variable, if that equals the opposite of that, so if you do a derivative of the function with one variable and with respect to the other, if they equal each other, then that's known as a state function. Sometimes it's referred to as a mother function. Sometimes it's referred to as path independent. They all mean the same thing. State function, mother function, path independent, all mean the same thing. And what that means is, so like it says path independent. So the amount of, I've used this last semester talking about like enthalpy. So heat of reaction or internal energy, how much energy is available. So if I have a gallon of gasoline, with the first law, remember the first law of thermodynamics. First law of thermodynamics is basically conservation of energy. And the change of internal energy of the system equals the work plus the heat. That's just for chemistry. If you study other classes, you can include other terms like you can include gravitational potential energy, for instance. We don't include gravitational potential energy in this class. So we're just looking at the chemistry. We're looking at the molecules. We're not looking at other terms. But but if you take a gallon of gasoline, and I can take that gallon and I can burn it to form, I don't know, 1,000,000 joules of energy. I'm just making the numbers up. So I can get 1,000,000 joules from this certain amount of gasoline, or I can put it in my car and I can get, cars are typically about 20% efficient. So I can get 200,000 joules of work and 800,000 joules of heat. Or I can put it into a hybrid car and get, I don't know, like a third efficiency. So 333,000 joules of work and 667,000 joules of heat. So whatever it is that I'm doing, right? So, or I can put it into a fuel cell car and I can get 600,000 joules of work and 400,000 joules of heat. So but the idea though is that the energy change of gasoline does not change no matter what path I do, but the path, what I get out of it does change. So that's the idea with path independence. So that's the same thing for entropy. So entropy, it's the number of states. So, I mean, it doesn't matter how you get to that number of states, the entropy is the same. So, and then Gibbs energy is the same way as well. So Gibbs is also a state function. So, and when we do calculations, hopefully this will make more sense. And what's even more crazy about Gibbs is that that it's connected to the equilibrium, which I think is amazing. Okay, so then let's talk about the third law of thermodynamics. So let's talk about the laws of thermodynamics. First law of thermo is conservation of energy. The change of internal energy of a system is equal to the work plus the heat that the system does, plus any other terms if you have other classes. So like I mentioned, gravitational potential energy, for instance. So depending on your class, you can add more terms to the first law. Second law of thermo is entropy is greater than or equal to 0 for the universe. The entropy is always increasing. So, well, I mean, you can have no entropy change if you have no heat transfer, but there are certain cases even where you have no heat transfer, the entropy still increases. There's one, for instance, is expansion into a vacuum. So you increase the number of states, but you still have no heat transfer. So even then, you're still the second law would appear to be 0, but it's still increasing. So entropy is always increasing. Third law of thermo is that a perfect crystal at 0 Kelvin has 0 entropy. So and that makes sense because a perfect crystal has one state, and if it's 0 Kelvin, it means it's not moving. Therefore, then entropy, the natural log of 1 is 0, therefore entropy is 0. So, and a couple of years ago, I think around 5 years ago, they actually challenged this a little bit. There was, they did this and they took a perfect crystal at 0 Kelvin or close to 0 Kelvin, and there's an issue with this law because of the uncertainty principle. Do you remember the uncertainty principle? That the change in position, it's an ugly X. The change in position times the change in momentum is greater than or equal to h over 4 pi. If you remember the uncertainty principle. The problem is they took a really small item and put it close to 0, and they noticed that the position of the crystal started to, it had an uncertainty in its position. So although it wasn't moving, because here with the momentum being very close to 0 and known, that means that the position becomes uncertain. So the position started to become uncertain for this small crystal, and then that started to challenge the idea how many states we have. So it still had one state, but it was like I said, well, that was the argument that came to like, well, when we have this thing, the position actually becomes uncertain and we can't really determine where it's at. And if we determine it, then we also give it momentum and we ruin it, the perfect crystal. But, or at least we ruin the 0 Kelvin. But the one state still holds. So there's it didn't break the third law of thermodynamics. So I guess it's more of a postulate so than a law. A postulate is something you take without proof. Well, I guess the proof is the definition of natural logs, but kind of a foundational mathematical argument. But I mean, the truth of the matter is the third law of thermodynamics, it's more of a Jeopardy trivial question. It doesn't really have any application. First law of thermo has application. Second law of thermo has application. Third law of thermo is just more of a definition kind of thing. It defines kind of what entropy is. So how are you gonna questions? I like this stuff. I think it's kind of cool that we have like the deep foundational stuff. Guess I shouldn't apologize for that. Okay. So let's talk about entropy. So now, what another thing that kind of gives me kind of chills in a way is the way that that some of these things prove that space-time is not quantized. So well, let me go into entropy and let me give you an analogy. So let's say you have $1,000. Okay, so if you have $1,000, what you can do is you can keep that $1,000 in cash. So I can have $1,000 in cash, or I can get $1,000 and I can put it into a checking account and I can have cash alongside that. Or I can take $1,000 and I can put it into the stock market. I can put it into a checking account and I can keep some in cash, right? So these are the different ways I can keep money. So, or if you want, I mean, we can keep the analogy going. I'm gonna say I can put it in bond market or something. But my point is that you can put this money in different categories. So if you give atoms and or molecules energy, they can store it in different ways. So one of the ways, like a water molecule, for instance, and sorry, I guess I can mime it this way. Okay, so water molecule is kind of shaped, as a V, and if you give energy, it can move temperature. So temperature is translational energy. So this is moving around. This is temperature. It can rotate. So it can store energy is by rotation, and it can store, if you can see in the camera, I'll do it. It can do vibration as well. So I'm vibrating my fingers back and forth. So water, for instance, can store energy in these ways. So that means, though, water, H2O, is going to have relatively high entropy because it has lots of states. So remember, entropy means more states, higher entropy means more states. So giving energy to water, water is going to have a relatively high entropy. Now compare water to like a neon atom. So a neon atom, and I'm just doing a fist, it's just a sphere. So these noble gases, they're just spheres. So they're not going to rotate. They can't vibrate because like oxygen, O2, it can vibrate here with respect to each other. But two gas molecules, there's no vibration because it's just an atom. So also energy can be stored electronically. So you can have energy going up, elevating the excitation of electronic energy levels. That's another way you can store energy. So noble gases have that still. But so if you look at helium versus water, so water, rotate, vibrate, and temperature. Helium, though, only has temperature. Well, it has electronic energy too, but at a relatively low energy level, it only has temperature. So, and then if you look at these, so then compare helium to xenon, you can see that the entropy is increasing from helium to xenon. So the more massive atoms, they have more closely spaced energy states. So because of their momentum, they're heavier, and so they can move in various ways. And so what I think is interesting about this, and this is also not in the textbook, this is one of the proofs that space-time is quantized. So like, what we live in space-time. So imagine 2 points, point A and point B. Like, I like these kind of discussions. Like, so you go from point A to point B. Like, so what is speed? Speed is distance divided by time. And if you have to move, so moving something to move across space takes a little bit of time. If there were an infinite number of points that space can exist between these 2 points, you will never be able to get here because it takes a little bit of time to cross over that space. So because of that, space only exists in little tiny packets. So, and the same idea with entropy here, if there were an infinite number of places to go between 2 points, then there would be an infinite number of states, then everything would have infinite entropy. and then because of that, that would change the way that processes work. Also, with these noble gases, if you can see, the heavier gases, they have more choices. So if you have more energy, if you have the same amount of energy, the end it makes less sense if you just look at one. If you think of a mole of xenon versus a mole of helium, the mole of xenon, it's going to have because if you give a little energy to the helium, it's going to pew, it's going to fly. It's lighter. It's going to fly. It's going to have for the same momentum. Helium has more speed. Well, it has more velocity. So, which means it has to cover more space. Xenon, on the other hand, it's heavier. For the same momentum, it covers less space. So since it covers less space than helium, there's more states, there's more places it can be. And since it can be more places, more states, that means higher entropy. So that's, I think that's cool. Like that explanation, you don't necessarily have to know that, but I think it's interesting because it shows that space-time and space-time, however you want to say it, space actually only exists in little tiny partition. Well, in quanta, it exists in tiny whatever existences. So another one here, if you look at argon versus nitrogen monoxide, argon is 40 grams per mole, nitrogen monoxide is 30 grams per mole, and the entropy is higher for nitrogen monoxide than argon. Why is entropy higher? We just mentioned here that the heavier atoms, or well, I guess atoms, and you would think that a heavier molecule, or a lighter, I should say, a lighter molecule is going to have less entropy than a heavier atom, and we find out the opposite is true. So why is that? And that's the argument then for the different like states. Like so, if I give argon $1,000, and argon can only put that money into cash, and nitrogen monoxide though, so nitrogen monoxide, so yeah, it can rotate and it can vibrate. So it has vibrational energy, it has rotational energy and temperature. So it's like nitrogen monoxide has cash in its wallet, it has a checking account, and it has a stock market account. So since it has those three things, it has more states. So does argon have states with its $1,000? Yes, it can have one $1,000 bill. It can have 10 $100 bills. It can have $900 bills and five $20 bills. So it has states for its temperature, but nitrogen monoxide is going to have more. It could do the same thing with the cash that argon does, but it could also put $500 into its checking account. It could put $100 into its money market account. So because it has more energy equivalent states, it has higher entropy. Kind of like, and I'm doing the analogy of money versus energy. So since it has other things it can invest its energy in, just like it's like a money accounts, it has more of the same number of energy equivalent states, therefore entropy is higher. So is that making sense? Or I guess I'm looking at your faces, you're looking a little confused, or is it just sinking in? Okay. All right. The explanation isn't as important. I'm just, I think it's cool. That's why I'm talking about it. But the so whats are coming up with the equations. So some of the other terms, so since entropy gives enthalpy, since these are all path independent, you can use these equations that we used in the first semester. Sorry, I think I spit on my iPad, and there we go. You ever notice that if you get something in your iPad, you can't zoom in anymore? So I should say it, not spray it. But because of its path independent, we can look at the end state, so final minus initial, the sum of the moles of the products entropy of the products minus the sum of the moles of reactants, entropy of the reactants, equals the overall entropy for the reaction. And same thing for Gibbs, and then using the whole delta G equals delta H minus T delta S, we can just calculate the other ones that way and then just plug it in. Oh, and did I talk about standard states? I guess I did in the first semester. So standard states, these degrees, that means standard states. If you remember from first semester, it's what we pick it. And the standard state that we pick is 25 degrees Celsius and everything being at 1 atmosphere of pressure and 1 molar of concentration. And it's interesting, especially with politics right now. I think I mentioned it in the first semester. Russia has a different standard state than we do. Same temperature. I think it's the same temperature. I'm pretty sure it's still 25 degrees Celsius, but it's they use a pressure of 1 bar instead of 1 atmosphere. So 1 bar is 100,000 kilopascals, and an atmosphere is 101.3 kilopascals. So our standard pressure is slightly higher than Russia's. So if you were to go to the Russian Federation, your standard states might be a little different than we have here in the United States and then all of Europe. So, but although with recent collaborations prior to Ukraine conflict, mainly in space, Russia may have adopted our standard states now instead of theirs. So maybe that's no longer true. I don't know. Obviously, we're not talking. So, all right. So let's use these for his equations. Calculate the standard change in free energy for reaction using standard Gibbs reaction is equal to the standard enthalpy change minus the temperature times the standard entropy change. So let's use the formation of sulfur trioxide from sulfur dioxide. What is the standard Gibbs energy change for the reaction at 25 degrees Celsius? Determine if the reaction is spontaneous. Okay, so those things, remember the delta H is going to be the sum of the N of the P, H of P, oh, no, yeah, that's right, minus the sum of the moles of reactants, H of reactants. So this is going to be equal to, so products, it's going to be H SO3 minus the quantity, so HSO2 plus 1/2 HO2. And I'm getting the stoichiometric ratios, those are the ends. So it's 1 for SO2 and SO3, and it's 1/2 for oxygen. And then you just plug in the numbers, HSO3 minus 395.7 minus the quantity minus 296.8 plus 1/2 times 0. So remember, enthalpy, H, is a relative term, and we pick the relatives to be 0 at elements and specific elements. So diatomic oxygen we pick as a 0, for instance. Let me go here. Okay. So in that's too far ahead. Here it is. So then H then is going to be equal to minus 98.9 kilojoules. That's an ugly J. So then delta S, same sum of N of P, S of P minus the sum of N of R, S of R. Same idea. S, SO3 minus the quantity S, SO2 plus S, or 1/2 SO2. Well, this time though, O2 is going to have an entropy. So equals S, SO3, 256.8 minus SO2, 248.2 plus 1/2, 205.2 equals minus 94.0, and the units joules per Kelvin. Okay, so now we then do the delta H equal, I'm sorry, delta G. What am I doing? Delta G equals delta H minus T delta S equals delta H minus 98. I always write out the joules. 98.9 kilojoules is 98,900 joules minus a minus 94 joules per Kelvin, and I'm running out of space. I'll move this down here. Oop. So I can write bigger. Minus a minus 94 joules per Kelvin times 298 Kelvin. And I'm kind of emphasizing this for the units because we typically put H in kilojoules and then S is in joules per Kelvin. Don't forget to multiply by 1,000. And when we do this, we get minus 70.9 kilojoules. And since it's negative, that means it's spontaneous. So, okay. And let's do a recap for this. So we have formation of SO3, which turns into acid rain. So this reaction in the atmosphere, is this going to happen? And we probably already know what's going to happen. So we don't know the Gibbs energy, but we know the enthalpy and entropy terms. So we calculate the enthalpy of the reaction. So the sum of the moles of products minus the enthalpy of products minus the moles of reactants, enthalpy of reactants. And doing so, we get minus 98.9 kilojoules enthalpy. It's very exothermic. Then the entropy. So look at the sum of the moles of products, entropy of the products minus the sum of the moles of reactants, entropy of the reactants. And we see that the entropy decreases by a factor of minus 94 joules per Kelvin. So then we take those numbers, apply them into the delta G equals minus, or delta G equals delta H minus T delta S. And then those numbers yield a negative 70.9 kilojoules. And that negative number tells us that this reaction is spontaneous. Another point, another fine point, are we surprised that the entropy is going down? I'm personally not surprised because we're going from, so SO2 plus 1/2 O2. I know it's not using proper form, but the moles of gas that we're having is decreasing. So we're going from 1.5 moles of gas to 1 mole of gas. The moles of gas is decreasing. That usually implies a change in a negative change in entropy for the system. So entropy is going down. Not surprising. So these are the kind of things also you can kind of go through in a check. So any questions with this? So I mean, I know I'm trying to combine all these concepts back and forth, but The main point with this, though, is that you can follow and use the equations, right? So one of the things I'm hoping you get is from this is learning different ways to use the equations. And students usually like this. It's very straightforward. Very straightforward. So let's see if you can solve this. We have 2 calcium plus oxygen makes 2 calcium oxides. And delta H equals, oh, geez, I keep on using delta H. Delta G equals delta H minus T delta S. Temperature is 298 Kelvin. You guys still working or trying to watch you engage your I thought I was going to finish this lecture today, but I guess I spent too much time talking excitedly about thermodynamics. I thought I'd hear the day. Some people think A, B, C. Oh, you guys both. Okay, awesome. I thought you guys were still working. Look, you're playing your phones. Yeah, C is the right answer. I was reading you incorrectly. All right, so how are we doing for time? Yeah, we'll have to pick this up next time. There's no way I can talk about this in less than 4 minutes. So this is, next one we're gonna get to is Hess's law, which actually I like Hess's law. A lot of students don't like it. It's a puzzle. I like solving puzzles. But okay, I think I'm gonna end class 3 minutes early then. Does anybody have any questions? No. Okay. I will end class then. Do you have any questions, Kiana? Nope.
No, I'm all good. Thank you.
All right. I will